Helsinki 2006, then went to Heidelberg for his postdoc with Christoph Batterich, and then had a postdoc at Utrecht, and is now in Oslo. Today he will speak to us about cosmologies with a new coupling, please.
Thank you very much. It's great to be here. I'll talk about this topic, which is one line of my research that I'm actively pursuing at the moment. So it will involve a lot of work in progress and possible comments and criticisms can be particularly useful. The starting point is a basic question, kind of fundamental question. What is the relation between physical and gravitational geometry? In general relativity, gravity is geometry of space-time described by the metric tensor G, and it's assigned dynamics by this Einstein-Hilbert axiom. Then matter fields live in this space-time and see some geometry, but whether this geometry has to be the same, I don't think there's any fundamental reason for this to be the case. In Einstein's theory, it is assumed, which is basically the postulate of equivalence principle. But one can consider more general relations. Just in order not to be unnecessarily complicated, we can assume that this relation is given by a single scalar field phi. It has been then argued that the most general consistent relation has this form. It is covariant because we don't want to give up Lorentz invariance, and it depends only on, at most, at the first derivatives of the scalar field, because we don't want to give up the second order nature of the theory and introduce any ghosts. Furthermore, I could add that both of these functions should be positive to avoid instabilities and superluminal propagation of signals. This C here is the conformal transformation that is very well known, and this talk will be about this function D, and I'll try to address these questions. First, I will argue that it appears quite generically in physical setups, and perhaps surprisingly, despite the implied equivalence principle violation, it is viable. And then I just briefly mention some implications to the parametricized post-Newtonian limit, but we'll talk much more about cosmology. And in the last part of the talk, I will present an explicit new kind of string scenario where this coupling arises. First, let us recall the conformal transformation. A prototype extension of Einstein's theory is given by drastic theory, where the scalar field couples non-minimally to the curvature. This non-linear extension of Einstein-Hilbert axiom, the so-called FR class of theories, is very extensively studied recently, and one can immediately see that it's just an example of this drastic type of theory. An example where this kinetic term for the scalar field happens to vanish. So this is the Jordan frame description. In string theory, this can be called the string frame, and this phi field can be the dilaton. But in both contexts, it's well known that by performing this rescaling of the metric, the while rescaling, that is a conformal transformation, we can bring the theorem into this form, which is completely equivalent. This is the so-called Einstein frame description, where now gravity is minimally coupled, but matter is non-minimally interacting with the scalar field. Now, if we consider any other extension of GR written in terms of curvature invariance, the corresponding transformation will involve also this formal part. And similarly, if we consider any scalar tensor theory beyond this restricted drastic class of theories, we have to take into account a non-trivial function d in this transformation. I have a footnote here about them. These higher derivative extensions of GR, because you might know that they are rather generically placed by ghosts, but as we recently reported in our letter, if we have infinite derivative extension context of non-local gravity, we avoid this. And furthermore, there's some evidence that such theories can be renormalizable, but that would be another story. Now I'm just going to give a couple of examples about how this formal transformation appears. So let's write down a theory involving this Ricci tensor squared. I consider it in the first order formalism because that's another way to avoid the higher derivatives ghosts. In that framework, the space-time connection is a priori independent of the metric, and we get equations of motion also for the connection. And what that equation of motion tells us is that the space-time connection is the Levi-Civita connection of this metric. There's a conformal relation to the gravitational metric, and in the case of non-trivial dependence on this Ricci tensor squared, indeed, there's also this formal part. And let's look at the scalar tensor context then. It has been recently quite popular to look at this so-called Horn-Densky class of tensor theories. That's the most general class of theories that has second-order equations of motion, even though higher derivative terms can appear in the action. So in fact, all viable scalar theories should have this form. One context where non-trivial higher order terms appear is that of massive gravity developed by Ram and Tolle and people here in Stockholm. There you get so-called Galilean-type scalar field terms, which belong to this class. But okay, I just mention perhaps the very simplest example, where both the conformal function c is unity and the disformal function disformal function d is unity. The Einstein frame theory of this, well, the Einstein-Hilbert action for this is nothing but the so-called covariant Galilean with non-trivial function g4 given by the square root of 1 plus the kinetic term. So let's then look at some consequences of such couplings. If matter is coupled to this Bard metric, the physical consequence is that the trajectories are extremized with respect to that metric. In other words, matter follows the geodesics of the Levi-Civita connection of that metric. There's the conformal factor that relates the proper distance, because that is the local change of scales. And in addition, there's a direction-dependent disformal effect now that's given by the projection of the forward velocity along the gradient of the scalar field. We can always write these additional effects as effective fifth forces. Just formally rewriting the geodesic equation like this. And we get an idea what this means. Let's look first at the conformal prototype. Again, the drastic theory, which is very well known. There, the fifth force is described by effective Newton's constant, which has this form. But now, the equivalence principle has been very well tested by Earth-type experiments up to the order of more than 1 times 10 to the power 10. So, does this mean these kind of scalar interactions are immediately ruled out? There are some ways out. The field can be very massive, and then the range of the force will be tiny, and we don't get at least any non-trivial cosmological phenomenology. And more or less the same things if we tune the coupling strength alpha to be very, very small. Then people have considered more or less artificially the case that you only couple dark matter non-minimal. But a particularly interesting case is when these couplings and the mass depend on the environment. That's the so-called chameleon. And briefly reviewing in this slide. So for gravitational experiments, the relevant setup, it's basically all the high precision measurements more or less broke, is spherically symmetric non-relativistic matter source in solar system. The solution to the equation of motion tells that the scalar field tensor decays exponentially beyond the Compton wavelength, which is given by its mass. Now, suppose we have a potential like this and this exponential form of the coupling. The effective potential now has also a contribution from the coupling. So, in very low density regions, like in cosmology, the minimum is formed here, and we see that the mass, which is given by the second derivative of this potential, is very low. So then we can have very high range forces and non-trivial phenomenology. However, in high density regions, like in our solar system, the coupling changes the effective potential in such a way that the mass becomes much, much higher. So that's how the field can be hidden in high density surroundings, and that's why it's called chameleon mechanism. This has been found to work and to appear in a general relevant context, but Obviously, you have to choose suitable forms for the potential and the coupling, and in order for this to be just hidden here, but to have cosmological consequences, you have to also choose the scales involved in a suitable way. But now I go to this disformal mechanism that we just recently reported in our letter. So I'll focus on this function d. Again, let's look at spherically symmetric static configurations with non-relativistic matter sources. The coupling is given by the contractions of the scalar field gradient and the energy momentum tensor. But because in these relevant setups, basically only the time component of the energy momentum tensor is non-zero, we can only have contractions with the time derivative of the scalar field. And since we are in a static configuration, here the happenings in the solar system can pretty much decouple from the cosmological expansion. It's rather immediate to see that this coupling vanishes identically. And now this is just due to the form of the coupling. We haven't assumed anything about the potential or the scales or the form of this function d. We can look a bit more carefully at this approximation. Take a high density limit. This form of function times the density is assumed to be much bigger than unity. Then the Klein-Gordon equation assumes a very simple form. Here in the second equality I have assumed again a exponential form for the coupling, just for cases of illustration. And the condition for the field to slow down, as we require for it to be static in this approximation, is just given by the condition that the slope of this exponential is positive. Furthermore, what we see from this Klein-Gordon equation is that unlike in the conformal case, the evolution is independent of the matter density. So we expect that the field doesn't form any appreciable gradients. It really just smoothens out. However, in cosmology, we do get effects from this coupling, because there we are not in a static configuration. Due to the expansion of the universe, there's time evolution. As we come to that. But, well, I just briefly mention that it will be interesting to study this more carefully when we deviate from this static spherically symmetric setup in several astrophysical situations. Maybe we do get non-trivial signatures and useful constraints. There's a promising student, Annu Myrhinen, at the Helsinki Institute of Physics, working now full-time on this. He's supervised by me and Kari Enqvist. But, yeah, I'll go to cosmology. So, we know that the universe is accelerating and there's some kind of dark energy that's supposed to be responsible for that. Here I construct the toy model where the dark energy is given by a scalar field phi. So it's a so-called quintessence field. And dark matter, I couple in this disformal way in order to see what are the consequences of cosmology. So for simplicity, I set the conformal coupling trivial and just choose exponential forms for the coupling and the potential. For reasons of simplicity, and also choosing these kind of forms because these exponential suppressions at play. All these dimensionless parameters, d naught, v naught, and a couple of slopes we have here can be of the supposedly natural Planck order. They are order 1 in Planck units. And when we look at the dynamics more carefully, we see that there are only 2 parameters in addition to the usual lambda CDM model. Writing down the Friedman equations, they look just like usual. The new modification appears, of course, in the conservation equations. There's this coupling term that in the Friedman-Robertson-Walker background takes this form. So in general, these kind of quintessence dark energy models have been considered because there's a huge fine-tuning problem with lambda, but if one assumes that the lambda is set to 0 by some symmetry principle, one could perhaps get more naturality observed kind of energy density if the field was evolving dynamically. Moreover, there's the coincidence problem of why dark matter density and dark energy density seem to be equal just today. If we have this kind of coupling and these densities can talk to each other in a non-minimal way, perhaps we can alleviate this problem. Moreover, with this kind of exponential potential, in fact, the dark matter and dark energy densities have been always of similar order of magnitude. This is the so-called self-tuning property of exponential potentials in cosmological backgrounds. The dynamics with such a potential are such that we can start from practically arbitrary initial conditions and we converge to an attractor where the quintessence field precisely mimics the background component. So it has the same equation of state. So that's why the densities evolve together. But well, if this field would reside forever in this attractor, we would never get acceleration, but we would just have equation of state 0 during the dust dominated era. So what sets now the acceleration going on is this coupling. In fact, the scaling attractor is not attractor in the dynamical systems terminology, as one can see by performing the phase-space analogy, but phase-space analysis. But in the case that the slope of the coupling is bigger than the slope of the potential, this point becomes a saddle point. So during the matter-dominated structure formation era, this coupling will become important and set the acceleration ongoing. So it freezes down the scalar field and it begins to behave like a cosmological constant. Now also, because of this new kind of coupling, dark matter begins to freeze. It lives in this barred metric, which is modified by the disformal function, and the time lapse is given by this formula. And it is going towards 0 asymptotically. So clocks made of dark matter will tick slower and slower, doesn't go to infinity, they will slow down. But what is reassuring to see is that they never turn pathological. This just approaches zero but doesn't flip its sign. This is a physical coupling. In fact, it's also a good cross-check. I have observed this kind of behavior in other setups. And if we get singularities, it's a sign that there's a typo in the code or in the equations. So we can then test this coupling by comparing the predictions of the background expansion with cosmological experiments. We basically use all the relevant data and the latest data sets. At low redshifts, the expansion history is most accurately probed by the supernova type IA, luminosity distance, redshift diagrams, and at about redshift 1100 there's the CMB, whose distance to us gives one very useful data point. Basically, the geometric distance is given by the location of the first peak in the spectrum. I'm comparing it with the scale of baryon-acoustic oscillations at lower redshifts. We get quite useful complementary constraints. In addition, we used data on the present Hubble rate from the Hubble Space Telescope and the predicted baryon fraction from nuclear synthesis calculations and observations. And what we find is that the model fits data as good as lambda CDM, not in any statistically significant way better. And we can only find lower bounds on these two parameters, the slopes of the coupling and the potential. That's basically because, well, for the potential, the amount of early dark energy, the contribution of the scalar field during the radiation domination and matter dominated era is given by the square of the inverse of the slope. So the steeper the potential, the less dark energy we have those times, and closer the expansion resembles the standard lambda CDM evolution. Also, the steeper the coupling, the more efficiently this freezing I described happens, and that's why the field begins to resemble a cosmological constant in a swifter way, and you see less and less difference to the lambda CDM model. However, despite the similar expansion history, the models are physically very different, as is obvious from the fact that dark matter also begins to behave like some lambda term. So to see more cosmological physics, we have to consider perturbations. I will just go with this more technical slide, but it's conventional to introduce fluctuations about the Friedman-Professor-Walker geometry in the longitudinal Newtonian gauge. Again, the perturbed field equations look just like usual, but the new effects appear in the conservation equations. They look like this for the two coupled components. We have the fractional overdensity delta and the velocity perturbation of the matter flows. And of course, the Klein-Gordon equation for the fluctuation in our scalar field. the background coupling term Q naught appears in these equations as a new term, but in addition, because already the dark matter density was modified at the background level, in linear perturbation theory we have this perturbation of the coupling affecting the continuity. And in this disformal case, this has very rich structure. It involves the density and the fluctuation in the field, but in addition, these metric potentials and some time derivatives. I'll present these functions explicitly here after some simplifications and solving away the higher derivatives. But you just see that there's a lot more going on than in the conformally coupled case, which is basically a single function if this form of the coupling is exponential. A single term. And you can always bring it into exponential form by redefining the field if you want. We can make much more sense of these equations even analytically. It's rather remarkable by going to the Newtonian limit. And that's actually the observationally most relevant limit, because the matter power spectrum we observe is pretty much within the horizon. If you go outside the horizon, due to cosmic variance and due to systematics, the error bars grow up very quickly. So, let's look at Fourier modes that are smaller than the horizon scale. Here we can then also neglect some time derivatives because the overall time scale must be given by the Hartree expansion, whereas the scale of the spatial gradients is given by the Fourier mode K. And at this limit, one sees that the coupling takes quite neat form. It's just the background coupling times the perturbation in matter. Using the conservation equations and the field equations, we can then work out the first, well, a second order closed differential equation for this matter density. We see there appears a friction term and an effectively time evolving gravitational constant. In the case of conformal coupling, we can see that this gravitational constant reduces as expected to the well-known drastic form I showed in one of the first slides. In the disformal case, we have this kind of more complicated function determining the evolution. But what happens in this exponential toy model is that we find the fifth force becoming much bigger than the force of gravity during the structure formation era. And this can be used to rule out this kind of model. I plotted the CMB spectrum here. You see that it's quite different from the observed one due to the enhanced integrated Sachs-Wolfe effect, because now the growth of structure is very strongly enhanced by this fifth force. You get more matter lumps, and consequently gravitational potentials evolve much swifter, and as photons travel through them they get redshifted a lot. And even more drastically you can see this effect in the matter power spectrum directly in the spectrum of cold dark matter. Here I however just plotted the baryonic spectrum that we can observe more directly, but even then it's obvious that or this model doesn't fit the observations well. This is the difference with respect to lambda CDM model plotted here. So just a couple of remarks about this instability. It's known to appear generically in conformally coupled models, as I found out in my thesis. And in fact, if the coupling is strong enough to address the coincidence problem at the background level, why the dark matter and dark energy densities are similar or why the acceleration starts just a day. If it's due to a conformal coupling, then you spoil the structure formation. And we recently found that if you use vectors or higher order forms, you get actually a new kind of effect. Dark matter is not any more than completely cold, but effectively you get pressures, and these can constrain the coupling even stronger. The question is now, with this much more richer structure, is this instability generic also in the disformally coupled models? Well, I think it's not. And one simple argument is that, as I also found in my thesis, that using the Gauss-Bonnet term coupling to a scalar field, you avoid this problem. And now, as I argued, when you do this formal transformation, or when you bring this Gauss-Bonnet gravity into Einstein form with the effective matter couplings, you have to use this formal transformation. So the corresponding this formally coupled theory should be viable. Yeah. Now I go to the last part of the talk, and that's about instead of these toy models to perhaps more robustly derive these kind of models which might then also behave perhaps more realistically in cosmological setups. So the framework is flux perturbations in type 2 string theory, the so-called DBI setup. The crucial thing here is that we get warping. The geometry is depicted in this figure. We have compactified the 6 dimensions. It can be a Calamity 3 space, and you can have all sorts of objects like D7 brains wrapped around there. But let's just look at the one D3 brain, because this brain should fill up the large dimensions. This D3 brain appears just as a dot in this picture. And because of energy densities due to fluxes, for example, we can form this kind of throats in the geometry, and now the brain can be floating around there towards the throat, as in this picture. And it's known that at least D3 brain, not being too big, can be treated as a probe in this geometry, and it obeys this kind of DBI action, where mu is given by the tension of the brain, and we integrate over the world volume coordinates of the brain. And there's the induced metric, and this, well, some bosonic fields appear in the theory. There's the bulk 2 form and SNS and a U1 gauge field on the brain. So in this setup, the disformal metric arises from the pullback of the geometry. Yes, cartoon of the brain, we have the coordinates xi. They are aligned with the large dimensions in the static case also. What the rest would be. And transverse coordinates depend on the location of the brain. For simplicity, we assume that it only depends on one coordinate. The D3 brain would be depending on one radial and 5 angular coordinates, but usually it's just predominantly moving in the radial direction anyway. And this radial direction is basically the scalar field we have. And well, this is the 10-dimensional geometry, and the warp factor, which arises due to the non-trivial geometry induced by some energy densities, is this function h. And basically this disformal relation arises as a pullback metric on the wall volume of the brain. The conformal part comes from this 4-dimensional part, and the rest of the stuff, the trapped dimensions, because of some possible non-trivial radial dependence, give us the disformal part. And now, whatever matter there's on this brain will be disformally coupled. I will give a concrete example soon. And these two functions c and d, they are obviously both determined by this warp factor. I will give a concrete example here. A couple of well-studied geometries in this setup are the Klebanov-Strasler, which arises from fluxes, and also this ADS 5-type geometry that arises from a stack of brains. It's not completely realistic, it's not compactible, but it's a good and useful approximation to the geometry of the drop. And moreover, it's known to have this very simple warp factor, so I choose to write that down. This lambda here is the top coupling. And as I said, the scalar field is related to the radial coordinate, the canonical one is just given by this tension of the brain. And that's the DBI action I wrote down. Let's now focus on the geometric part, which is, so forget about these gauge fields now. Well, when I just write down this determinant, I get an action for a single scalar field like this. Oh, this is the kiloton which gives the string coupling, but as usual I assume it is stabilized, this curly phi. In addition, we get this 1 per h, which comes from the charge of the brain. That would come from the West Jumino action, but I didn't write it down. Well, we can get a potential also. One simple case, it's we can imagine an antibrain in the tip of the throat, and then there would be a column force and column potential 1 per 5. But one can consider couplings of the branes to different sectors, and in each case, in principle, compute explicitly also the potential. So that's the geometric part, which involves the scalar field. And then, as an example of matter that this scalar field would be formally coupled to, let's take this F term here. It's already there. So it seems like a natural thing to consider. Its interpretation is that it's due to open string endpoints on the frame, and they will couple to about two forms, again through the best terminal action that I didn't write down, but anyway, they, due to this coupling, they get masses by absorbing the 1 degree of freedom. Consequently, we have massive fields on the frame. They can decay to some other particles, but what is an automatic outcome of this is that these particles are dark. They are distinct from our stack of branes, where our standard model gives this is separate brane, a sort of invisible sector, and also, as we saw, they are automatically disformally coupled from our point of view. So now this is the way to get a kind of 5 DDM model where this field phi is given by the location of the brane. So it's the transverse movement of the transverse oscillations of the open strings. And if we identify dark matter with these vector fields that are there, then dark matter in this picture would be the oscillations along the brane. But I end this talk soon, so it remains to be studied how we can constrain this explicit setup with cosmology. The questions of interest are, for example, if we can now have a viable dark energy model without this fatal instability, even if this phi field doesn't now provide us with acceleration, it's interesting in any case that we can probe we can test the possibility whether dark matter is on a moving brane or not by looking at precise data on structure formation. And since we do get new small scale effect in very good, well, in lucky case we can then alleviate the problems of the lambda CDM that have been at least claimed to appear at small scales. The most accurate data will come eventually from Euclid. I have been working on that for a couple of years now, though I didn't have time to go into that. And I'm working with David Motta in Oslo and his postdoc, who's expert in n-body simulations on the nonlinear predictions of these models. And I continue to work with Mikael Chumala-Kareki, who's my former student. He wrote his thesis on these disformal couplings. Now he's continuing as a postdoc in Heidelberg with Luca Mendola. So now I've talked for 45 minutes. Let me summarize that. Just a couple of basic points that these disformal couplings they are very generic in gravitational theories, though huge amount of attention has been upon these very restricted classes of FFR theories. You consider anything else, you get the disformal output. And we had this string setup where the coupling arises very generically, though its consequences hadn't been somehow this far investigated in cosmology at all. And this coupling can be viable because there is a new kind of screening mechanism that seems to take place almost automatically. And eventually we can use Euclid to probe the consequences of the cosmological models to large-scale structure. Thank you very much for your attention.
Thank you. Questions, please. Yes, please.
So you have this screening of the forms when you have high density regions. So does that mean that if you look at like just the point mass, then the density is for zero outside, you would then not get the screening, or?
The screening actually doesn't rely on having high density.
Okay.
It comes from assuming spherical symmetry, no pressures, and no time evolution. Then I went to this high density limit because that's relevant to solar system. High density with
Okay, so
with
this is
in
different
comparison
from
to cosmology.
other medium models where you actually, okay, so you don't need the high density to get the screening here.
No,
Okay, good.
and no specific forms for the potential or for the coupling.
Okay.
Any other questions?
You talked about this disformal dark matter. At the very end, you said that it could be some oscillations on the brain. Do you have any more concrete? Because anyway, you showed that the disformal dark matter 22%, so it's a complete model. Is it?
Yes.
In what way could it be observably different from what we say cold dark matter?
Well, the equations are here. You get this.
Explain that.
Yeah. Due to this non-minimal interaction, we get modified large-scale structure. In this toy model, we got also quite different for background evolution in cosmology, but in general we will get modifications to the formation of structure. I haven't computed it explicitly yet for these particular setups which we derive from string theory. I have only computed it explicitly for this toy model, and there you certainly see that we get effects. In fact, we can rule this model out.
Yeah, I understand that, and this is in the linear regime. I was rather thinking in the non-linear regime, for example. Really gravitational collapse with this.
Yes, that will be very interesting to study because, well, in the very small scale limit we have this screening mechanism at play, and the effect will disappear. But at cosmological scales we have this new stuff going on. So what happens in the intermediate regions on scales of galaxy formations and nonlinear clustering. That will be interesting to study, but that's what we are just beginning to do with well, the anybody guys at Oslo.
So it would be fair to say that you don't expect anything to happen in the very small scales, but this could have effect on, say, Nash function at some
Yes,
point.
certainly.
That would be an observable by which to distinguish. Right?
Any other questions? The complicated topology, non-trivial topology, does that have any direct consequences for the expansion of the universe, or does that affect dynamics?
Non-trivial topology of what?
Of the universe.
Well, we don't predict non-trivial topology in this setup, but
You should. I thought you showed non-trivial topologies. Maybe I misunderstood that.
where?
When you showed this picture with this road, for example, and the
Those are the extra dimensions.
Yeah. Yeah, okay, in this setup, yeah. Well, you can have all sorts of fancy stuff. This almost would correspond to non-trivial topology. You could have higher dimensional branes and so on.
yes.
I haven't really considered all these possibilities. I just focused first on this, well, simplest setup of 1D, 3 brane moving on. Yeah, there are, in principle, one could also study non-minimal setups, because this is a new kind of probe of string theory in principle. So you could compute what consequences non-trivial topology might have to this setup, but I admit I
Yes.
haven't
Okay.
considered it yet.
Are there any other questions? If that's not the case, then let's thank Tomi again.